Of Foundations of Math 20. We're going to be talking about 6.6 here, linear programming. Now, when we talk about linear programming, what we're talking about is we're trying to find out what the optimal solutions are to a certain situation. Now, we've worked all the way through Chapter 6 on creating something called a feasible region. So the feasible region would be the region within the constraints that would be, these inequalities here that we've put together on one graph. So it would be this region in here would be the feasible region. Now, the optimal solutions would be the points at or near the corners of this feasible region that would yield us either a maximum or a minimum for something called the objective quantity. And so in 6.6, we talk about something that's separate from the graph, and that would be a function like this. And oftentimes you'll see this instead of C as Q, the objective quantity, and this is what we're trying to optimize, either maximize or minimize. Now, in the textbook, you'll see that what they suggest that you do is you take a look at the points at or near the corners that are in the feasible region, and that you test them with the objective quantity, and that's what I've shown here. And so that's a fine way to do this. That's totally fine. I'm going to show you a way that's going to save you a little bit of time, and so that you don't have to try all the points. You can just get right to the point that's going to give you the maximum or the minimum right away. And so if you plug in the points, for example, 60 and 10, you plug in the points here into the objective quantity, and you're going to get a value for this quantity, and we change this to Q up here. And so this one here, 60, 40, is going to represent this value for our now Q. And then 30, 40 will give you this value for Q. And so you can see by comparing these which one is going to give you the maximum amount and which one's going to give you the minimum. And of course, it's these two right here. The point 60, 40 gives you a maximum value, and the point 30, 40 gives you a minimum. So that's fine. You can always do that. That's great. If you want to save some time and if you want to understand how linear programming actually works, this is what I want to show you today. And so what we want to do is we want to notice that this is an equation of a line separate from these inequalities. Now, how do we know that? Well, here's S and here's R. So here's R here, that's like the Y, and the S is over here like the X. So it's kind of like this. Q equals 12x plus 8y. And that looks an awful lot like an equation of a line, where Q is some constant. It's some number. And so what I want to suggest is if we isolate for y and show this as y equals mx plus b, then we're going to see that this constant is going to be related to a y-intercept of this line. And so real quickly here, if we've got 8y equals negative 12x plus q, okay, just getting this over to the other side, and I'm switching everything around, and I get y equals negative 1.5x plus 1/8 q. Okay? So what's important here is that this is now in y equals m, slope, x plus b. This is b, the y-intercept. Okay, that's really important. So what we're going to do is I am going to actually show you what this line, now remember this is related to our objective quantity. This is a line that is separate from the inequalities, and what we're looking for are points x, y, i.e. these ones, that will give us the largest Q value, i.e. the y-intercept. Okay? So I've made these lines, and I'm just gonna hang on for a second here. Okay, here are the lines. I'm gonna bring them over into our work here, if I can see here. Okay, so let's say something about like this. Okay, so we'll get back to a regular view here. Okay, and this is what we have. Okay, all right, now take a look at this. So what have I just done? Well, I've quickly drawn 3 of these lines. How do I know these are these lines? Well, the lines have a slope of negative 1.5. Okay, negative 1.5. And they go through, the first line that has a slope of negative 1.5 goes through the point 30, 40. The second one goes through the point 60, 10, and the third one goes through the point 60, 40. And so again, what you want to do is you want to draw as many lines as you need to go through the points that are on the at the corners of the feasible region. Okay, so what I'm going to do here is I just need to see that I just need to move this up so that you can see what I'm trying to do here. Okay, oh, this is not going to go real perfectly here. It's really tough to minutely move this. Okay, that's good enough. You got to get the point, right? These lines go through those corner points. All right, so what good does this do us? Okay, well, again, if you're looking for a maximum quantity here, maximum, and this is a plus q, or plus something q, a plus q, then all you're doing is you're looking for the y-intercept that represents a maximum here. So which one of these three lines gives you a y-intercept that's the biggest one? Well, it's this line, right? It's this red line. Which point does this red line go through? 60, 40. So guess what? The point 60, 40 will give you the largest q. You know that right away. So all you need to do is look at the slope of a line, and then move that line through each of the points, and whichever one gives you the largest q, if this is a plus, the largest q, that's the point that's going to yield you the maximum solution. Okay? All right, so let's do another example. Let's do another example here. Before I get to these notes here, let's do another example. Okay? Let's say we have this one. Okay, so here's our feasible region. We've got some points. Looks like here, here, and here. Very similar to the one we just did. Here's our objective quantity. So what you want to do is you want to isolate for y. Okay, let's get that y term all by itself. I'm going to move the 9.8 to the other side. I'm going to have negative 9.8x plus c. See that? Now I divide by 15.75. And this is what I'm going to get here. Obviously, I'm going to get just a y here. And what's this slope? Well, let's get out of there. If I have negative 9.8 divided by 15.75, I get negative 0.622. 0.622 x plus, now this is 1 over 15.75 c. This is a plus, and here's our constant. So what we do is we draw a line, a red line, or whatever line with this slope, negative 0.6. Let's see if we can do that. Okay, so a slope with negative point. Okay, so it's going to go down from left to right, and points connecting here would be 1. So 0.6 would be down 0.6 over 1. So it would look something like, I guess, this. Okay, and that's it right there. So what we're going to do is we're going to just see what does this line look like if I go through this point. Boom, right about. Come on. Okay, that's good enough. Close enough. All right, so it yields me some kind of y-intercept right around here. Okay, well, I'm going to copy this, and I'm going to put another line. This line is going to go through this point. You see how it's the same slope? Okay, I'm going to do another line, and this line is going to go through this point. All right, so you tell me, which line has the largest, because this is a positive, and here's our constant, and again, this represents the y-intercept of this line that is taken from your objective quantity. Largest intercept, this point gives you the largest objective quantity. So whatever point that is, 15, 15, that's the point that's going to give you the max. Okay? So max Q, or in this case it's C, sorry, max C at the point 15, 15. Boom. You don't have to test them all, you know what the max is. What's the min? The points, the minimum C is going to be at the point 15, 0. Minimum C at 15, 0. Okay? So again, that's all you need to do. You don't have to check all the points. You can check all the points if you don't like this. If you don't like doing this, that's fine. Okay? Okay, so here are your notes here. If you want to take these down or look at these at least, I'll read through them. So if you view the objective function as a line, and again, it's kind of a y equals mx plus b line, then the constant of that function, or of that line, is related to the objective quantity. That's the intercept. Okay? If you sketch the line that's related to q, then the max intercept will pass through the optimal solution points. The max intercept. The largest intercept will give you the points that give you the maximum solution. The smallest intercept will be through the minimum solution points. And that's if we have a plus C or a plus Q, whatever at the end. Now I'm going to talk about what happens if you get a y equals, something like this, minus Q. If you have something like that, it's going to change a little bit. I'll get to that in a bit. But I do want to show you one other cool thing here, and this is why this works so well, is that you can actually get these numbers right here, these maximum and minimum values that we see down here, 800, 1040, and 680. You can actually get those from doing this as well. So watch how this works. So what is the intercept here through this line? Well, if we look carefully, and if I did this completely correct, and this was the right slope through the right point, this shows up to be about 85. Okay? Now what's so cool about that? Well, 85, if this is 85, that equals 1/8 Q. Multiply both sides by 8, that means that Q equals 8 times 85. Guess what 8 times 85 is? That's 680. Okay? So you actually look at this, that's 85 times by 8 here. All right? What else? What else do we know? This one right here is going to run through this. I think this one's about 100. Okay? If you extend that up, that would go through exactly 100. Well, what's 100 times 8? 800. So this point, 6010, has an objective quantity of 800. You can get this all from the line and all from the graph. Very easy. And of course, this one here, this one would be about 130, I figured. And so 130 times 8 gives you this, 1040. It's exactly what you get. Okay? So that's a little bit on linear programming. I will talk to you here now about, let's see, this is the last question. Okay. So what happens if this is your objective quantity, and here we know that n is x, so this is x and this is y. If I solve for y, positive y, because that's what you usually, that's what lines are, right? Y. I get this, 2x minus q. So if we have a minus q here, then everything is opposite. Everything is opposite. So look, we have a positive slope here, and I'm just going to freehand this right now. Okay, so positive slope, it's going to be like this. Wow, that's not even straight. Like this, that's brutal too. And then like this, okay? Now for this objective quantity, as it turns out, this point gives us a maximum. And look, it has the minimum y-intercept. This point here, well, what did I do? There. Oh, I missed one. There we go, this one up here. So this point here has the maximum intercept, and it gives us a minimum. Okay, so everything's opposite when it's minus q. Okay, when it's minus q, and that is something that is sometimes missed here. So here's the important note there. Okay, if the line function has a plus q, then the intercept, as the intercept, then the max optimal solutions represents the max y-intercept. It's just straight on max and max. If it's the other way around, if it's a minus q in your objective quantity line function in y equals mx plus b form, then the max optimal solutions are the minimum y-intercept. So that's just taking into account the minus q there. All right? So it's a little different way to look at it. Once again, the bottom line is this. Bottom line. You can look at these points, you can use the objective quantity, and you can figure out what values are at every point. But you're going to have, sometimes you're going to have 5, 6 points. So do you want to test all of them and then look at the numbers and see which one's the largest or smallest? Or do you want to do a little bit of rearranging, find the slope, sketch that line, and figure out right away which point is going to represent your max and which one's going to represent your min? I'm just saying that this is pretty easy, and it's easy to do, and I think you should consider doing that. All right? So that's what the third step in the linear programming is, using these sort of lines and the intercepts to calculate. And here's, of course, this important note again. And a suggested assignment would be 1, 2, 8, and 13. You'll need to check with me or Google Classroom or a friend to make sure that that is your assignment for this year, this particular year. But anyways, where are we at here? I want to show you you want to take a look at this in summary, it's a little bit of a summary of what this section is about, not including the using the lines, because that's still something a little extra from me. Okay, that might save you some time. And here are the questions that you can practice with. Now for number 2, you're going to have to graph this, find the feasible region, identify the points of intersection, all that sort of stuff. So this one is from scratch. What's the maximum solution? From scratch.